Hi everyone, this is 12.2 day 1. And in this section 12.2 we're going to evaluate limits again, but this time algebraically. So in calculus, any problem can be solved in 3 ways: graphically, algebraically, and numerically. What we did in the last section was actually, we focused on the graphically part, because if we had to find the limit, what did we do? Graph the function, examine the graph, and determine the limit. We started off the lesson with the numerical approach as well. The numerical approach was when we plugged in values like this, and in order to see the trend. That is the numerical way. So here we did graphically and numerically. Today we're going to do the algebraic method. So we want to know, given a function, how to evaluate the limit algebraically. All right. So let's talk about limits first. All right. Let's start with the properties of limits, and we're going to start with the most basic function there is, the constant function. All right, so suppose you have a function y equals 5, right? What does that look like? Well, here's the x-axis, here's the y-axis. Y equals 5 is basically a horizontal line that goes through y equals 5, correct? That right there is y equals 5. So let's take a look at the graph of y equals 5 for a minute. If I wanted to find the limit of that graph as x approaches 2, right? So as x approaches 2, that's right here. To the left of 2, the value is 5. To the right of 2, the value is 5. Oh, so the limit is 5. Well, how about the limit as x approaches -3? To the left, oh, it's 5. To the right, oh, it's 5. Oh, so the limit is 5. And if you ask yourself, for any other x, is that going to change? It's not going to change at all. Now, is this only for the case of y equals 5? Or can the same thing happen for an equation like y equals 3? Y equals -7, or y equals k, right? Where k is a constant. So anytime you have an equation like this, y equals k, you're going to have the same situation where the limit, no matter where you are, is going to be that same value of k. And that's what our first property tells us here, that the limit as x approaches c of k, right? So from that, what does it mean? If I just see this, this is telling me I have a function y equals k, and I'm looking for the limit as x approaches some number. Well, if it's y equals k, then the limit is always that same value, k. So for example, suppose you're walking down the street and on a billboard you see this, just this, the limit as x approaches 2 of 3. What's the function here? The function is y equals 3. And because that's a constant function, the limit is just 3. Okay? All right. Now, let's step up one function. Suppose I have the graph of, what is this the graph of? Yes, it's y equals x. And now suppose I wanted to find the limit as x approaches 2. Well, if this is y equals x, when x is 2, y is roundabout, y is 2, right? So to the left of this, y is 2. To the right of this, y is 2. Or the limit must be 2. Okay? What if I needed to find the limit at x equals -4? Well, very close to -4, to the left, the y value is something very close to -4. To the right, the y value is something close to -4. So that tells me that if I need to find the limit as x approaches c of x, what's the function here? Y equals x, right? The limit is that value of c. So for example, if I have the limit as x approaches 3 of x, what's my function? Y equals x, right? And so think about it. If y equals x, whatever the x value is, the y value has to be the same. So for an x value of 3, the y value has to be the same number of 3. All right. So with that, we could actually build on some properties of limits. And we can use those properties to evaluate the limit of any function. Okay, so suppose you have two functions, f and g. The limit as x approaches c of f is L, and of g is m. Now, if I were to add those two functions, their limits would add. If I had to subtract those two functions, their limits would subtract. Multiply by a constant, same deal. Raise it to a power, same deal. Okay, we're going to use those for some examples. So for example, suppose I have the limit as x approaches 4 of x, right? We just said if y equals x here, then at x equals 4, the limit or the y value is close to 4. Now what if it's the limit as x approaches 4 of x squared? Well, when it was just x, it was 4. X squared is 4 squared, 16. Okay, so that's how we're going to build on the other functions. All right, so let's take a few examples here. For the first one, I have the limit as x approaches 2 of 3. So first, identify the function. What's the function here? Y equals 3. This is just a horizontal line. No matter where I am in x, the y value is always what? 3. So the limit here is just 3. Because I have a constant here, the limit is the same constant. Ooh, what about the next one? The limit as x approaches root 2 of e. What's the function here? Y equals e. Okay, what does that look like? Oh, e is also a constant. So what difference does it make if I have y equals 3 like in A or y equals e like in B? You know what the difference is? Nothing. It's another horizontal line just at a different point. So the limit here is e because that's a constant again. Okay, now let's spice things up a little bit. Let's find the limit of functions. We're going to first take two different types of functions. We're going to take polynomial functions and rational functions. All right, for a polynomial function, if I wanted to find the limit as x approaches c of p of x, that's just p of c. Hey, what does that mean? All you have to do is use direct substitution. That's it. Just take c, plug it into the function. Which means for rational functions, because rational functions are just two polynomial functions on top of each other, if I wanted to find the limit of f of x, I take that value of c and I plug it into the first function divided by the second function, right? So obviously here, because we have a denominator situation, this does not work if the denominator gives you a 0. All right, so how about this? Without further ado, let's just do some examples. All right, here's the first few examples. All right, number one. We're going to use direct substitution to evaluate the following. So, the limit as x approaches 2 of this function. We're direct substitution, so all we're going to do is we're going to take the number 2 and plug it in to wherever you see an x. So that's going to be 2 minus 3 over 2 times 2 squared minus 2 minus 15. That'll give you negative 1 over negative 9. And that's 1 over 9. Okay? All right, let's take a look at this one. The limit as x approaches to negative 1 of this. You take negative 1, plug it in there. The square root of negative 1 plus 3, root 2, which is about 1.4. Now I know somebody's asking, do we have to put it in decimal form or exact form? Depends on the situation, the directions, and so on, but in Precalc Honors, we have to be equally well versed in both. So now wait a minute. Is that really all it is? Can that be? Is that really the same as what we were doing in 12.1? Well, let's check. It just so happens that I have the graph of that equation right over here. Let's press enter. And now all of a sudden, this is a problem from 12.1. Okay, can it really be that the function, sorry, just a sec. Can it really be that the limit as x approaches to negative 1 is just what we did right here? Well, let's see. Let's go to negative 1, right? Remember what we were doing before? We were tracing and so on. Let's trace. And let's go to negative 1. So as I approach negative 1, look at what's happening to my y values. 1.5, 1.48, 1.44. Oh my God, it's totally getting closer and closer to 1.4. Well, how about if we do it from this side? As I approach negative 1, yep, 1.3, 1.34. Oh, 1.4. So, yep. Totally is the same. Okay? So all you could have done in the last section, rather than graphing, is just plug in the value where you're finding the limit. Keep in mind, however, that this is just the first, few problems of this lesson. Things are going to get difficult. These are just the, rosy peach-colored problems where everything turns out just fine. We're not even dealing with zero denominators and so on and so forth. All right? But let's keep things civil for a little bit more. Let's go to one more problem. The limit as x approaches negative 8 of this. Okay, let's plug in negative 8. What does that give me? Negative 8 plus 6. That's the square root of negative 2. That's not even a real number. Right? So because the limit is not a real number, we say dne. Okay? Does not exist. Now, does that make sense? Well, let's see. What does the square root of x plus 6 look like? If it's x plus 6, then there is a shift to the left of 6 units. And so it looks like that. Where is negative 8? Where is it that I'm looking for the limit? Right here. Okay, there isn't even a graph there. That's like barren country, right? So obviously the limit does not exist there. Okay. Oh, let's take a look at this one. Now we have the limit of this function, right? So that's the function y equals that number, that function. The limit as x approaches a. Okay, so what's the difference if it's a or 4 or negative 2? No difference whatsoever. Now I take that value of a, because that's just another constant, and I plug it into my x's. And so the limit will be 2a squared minus 5a plus 3. Who says we need actual numerical values? Who says we can't get a symbolic answer? All right, there you have it. that is 12.2, day 1. You can now go ahead and finish up your homework. Thank you very much.